In this video, we're going to continue the second part of computing the following integral. Exponential x between 0 and 1. We have said that this value is equal to e minus 1. We used the left Riemann sum and we proved that it's equal to e minus 1. Now we're going to use the right Riemann sum, okay, with delta x is k over n, and xk is a plus k b minus a over n, with a is 0 and b is 1, we get k over n, and delta x is just x plus 1 minus x sub k. So let's review this one. X k plus 1 minus xk, so it's k plus 1 over n minus k over n, which is 1 over n. So we proved it and we got it right, 1 over n. Okay, so 1 over n. So we in here we have the exponential. Okay, so when x is 0, which is a, we have 1. Okay, in the right Riemann sums, we're going to use this one here. So we start from 1. So we use this one here. So we're going to make this error by computing this extra area here in this rectangle. The same thing here. So the area, the exact area is this one, but in using Riemann sum, we're gonna add this one. Okay, how to do that? So let's call this integral, let's call this sum t. So it's, by definition, it's the limit as n goes to infinity is the sum of the area of the rectangles. It's 1 over n. Okay, the sum of f of x sub k, with k going from 1 to n. Okay, so here we know the x case, it's 1 over n. So when we plug that, so no, xk is k over n, sorry, delta x is 1 over n. So we're gonna plug the xk is k over n. Okay, and we're gonna plug this one here in using f. F is exponential x, so the expression becomes this implies that t is the limit as n goes to infinity of 1 over n, the sum of k from 1 to n of e to k over n. Okay, so here we notice that this one can be written as the limit as n goes to infinity of 1 over n, the sum from k going from 1 to n of e to 1 over n e to the power k. So this is a geometric sequence, okay, with the ratio is 1 over n. So we know it's sum, but from 0. So we have to add and subtract 1. So the limit of 1 over n minus 1 plus, look at this index. I'm going to change it from k going from 0 to n of e 1 over n to the power k. Because when k is 1, when k is 0, we get 1. And 1 minus 1 is 0, and we start again from 1. So let me write this expression again. So we have 1 over n minus 1 plus 1 minus e to the n plus 1, the last term of indices, the last sum over n over 1 minus e to 1 over n. Okay, so this is the limit that we need to compute. Okay, now we notice that if we let n get inside, because it's the sum of two limits that we are sure that they converge. Okay, we can say the sum of the limit is the limit of the sums. So here we have the limit of minus 1 over n as n goes to infinity plus the limit as n goes to infinity of 1 minus e. So I'm going to simplify this expression. It's going to be e to the power 1 times e to 1 over n over 1 minus e to 1 over n. Okay, you see this one here? This top part, it's e times e to 1 over n. So this limit here, okay, we know it's 0. Okay, 1 over n, you divide 1 among millions, they get 0. This one that we're gonna do, this one that we need to compute to find the value of the integral. Okay, I think I have a separate sheet for that. So I'm gonna study a function, because the limit here, if you try to do the limit, you get what? You get e to 1 over n. When the limit goes, when n goes to 0, you get 1. Okay, and here in the bottom, you get 1 minus 1, which is 0. So you can't have this one. Okay, so we need to do more work on this limit. So let me introduce this function. Okay, so I define this function as, so the 1 over x times 1 minus e to 1 over x times e over 1 minus x. So in fact, I changed n to x. Okay, and I defined a function because the limit of this function is the same thing as the limit of the sequence. But here, I want to find the limit as x goes to infinity of g of x. Okay, it's the same thing as the limit as x goes to 0 when I switch the variable. So I take 1 over x as u. So when x goes to plus infinity, u is gonna be 0. So I have u times 1 minus e to u times e over 1 minus e to the power u. Okay, so this is the limit. Why are we doing this? Because we're gonna use Taylor series. Okay, Taylor series, we will come back to that. You know them. So we know that e to the x, when x is close to 0, is given by 1 plus x plus other terms that they go to 0. So we use this function here. So e to the x is 1 plus x plus epsilon x, with the limit epsilon x when x goes to 0 is 0. Basically, we are saying when we are close to 0, e to the power x is behaving as 1 plus x. They act the same. This one is going to help us. Okay, so here we take we take the 1 to the left side and we divide by x. We get 1 plus this epsilon x. Okay, okay, this limit as x goes to 0 is 1. So we have the limit of this one here. So now we have this part, we have it as this one here. Okay, so we have it as this one goes to 1, and e to the power u goes to 1 as u goes to 0, Okay, so notice here we can write this one as the limit as u goes to 0 of u over 1 minus e to the power u times 1 minus e times eu. Okay, so we know from here, okay, when we flip this one, okay, it's 1. It's the same as this one. This one, as u goes to 0, it's gonna give us, so 1 times 1 minus u with this minus. The only thing that we didn't say is that this is minus this one. That means if this is 1, this limit is minus 1. So with the minus 1, so minus 1 times 1 minus e, it's e minus 1. And therefore, the limit of 1 over n sigma k from 1 to n of e to k over n, okay, which is equal to the integral, which is equal to e minus 1. sorry, e minus 1. So we have find this limit. And we said this limit is the integral, the right Riemann sum. It's e to the x dx, which is e to minus 1. So we have proved both ways, the right Riemann sum and the left Riemann sum, both equal e to minus 1. And therefore, this integral is equal to e minus 1. Okay? Remember to pay attention to these limits. Sometimes they're tricky. We're going to do one more concerning when we're trying to find f of x, arctangent of x between pi over 2 and pi of this function using Riemann's sum. Okay, we're gonna see that we need to have this definition of limits and be able to compute them. Thank you.